Okay, so these two formulas that you have here represent the surface area of a cylindrical can and the volume of a cylindrical can with the following dimensions. So here's how you sort of draw a sketch of this. Draw two circles, and here's the radius r. It appears in the bottom circular base, but it's also up here on the top as well. And then the height is how tall this thing is. So this first formula tells us the total surface area of that cylindrical can, and the second formula tells us the volume of that can. Okay. The way this problem is stated, they're telling us that the volume of the can is 355 centimeters cubed. So we're being told that volume equals 355 centimeters cubed, and they're asking us to find a formula for volume. And it doesn't really matter what this number is, actually. The process would be exactly the same. Let's finish. So what we can do here is we can take this volume, put it into this formula. So we get 355 equals pi r squared h. Actually, I made one mistake here. This is supposed to be find the volume not for V, but find the volume for surface area. Okay, and then they want it in terms of just the radius of r, in terms of r. So what you notice is the surface area formula, which is given to you, looks like this. SA equals 2 pi r squared plus 2 pi r h. And if you look at it, it almost fits the bill. Surface area equals 2 pi r squared. Well, there's just r right here. Okay, so we're happy about that. And then, this h is the problem. We don't want that h there because the instructions say write surface area as a function of r only. Well, since you know this equation, you can get rid of that h. If we solve this for h up here, we get h equals 355 over pi r squared. And there you go. So we could just plug that in here, and we'd have a formula that only had r in it. So we get surface area equals 2 pi r squared plus 2 pi r times 355 over pi r squared. Sure enough, you look through there, there's no more variable h anymore. It's been replaced. Okay. Now you can simplify a little bit, so you should do that. These pi's will divide to 1, and then one of these r's will divide out with one of those r's. So you get surface area equals 2 pi r squared plus 710 over r. Now, just one important thing you should know about this formula. This is the surface area of a cylindrical can that has a volume of 355 centimeters cubed. This formula would not work for a can that had a different volume than 355 centimeters cubed. So you know, it turns out that in later courses, particularly in calculus, there's a subject that you study called optimization, which means find maximum and minimum values of certain things. And in that particular subject or unit of study, it's very convenient to take your formulas and write them as a function of just one variable. You're going to want to do that. Okay? That you'll see later on why that's so. I'm going to graph that new formula and a window. And the window we're asked to graph it is for radiuses between 0 and 10. Okay. So our formula started. It was going to be 2 pi. Now in the calculator, make sure you put in x instead of r. It's not going to understand r when you're in function mode. So x, and we'll do squared, because that's what it was. We're doing the area formula. Okay, and then we have plus, and then it was 710 divided by x. Okay, so there it is. And they asked us to graph this for a radius between 0 and 10. So x is going to be between 0 and 10. Okay. So now we'll go to the window, and I'm going to make x min 0 and x max 10. If you're using a T89, you've got to press diamond F2 to get to the window. Now, as far as y min and y max, we're not quite sure what those numbers are going to be yet. So, I mean, Like you could start with negative 10 and 10, but most likely this is not going to be a good way to view the function. All right, so once you have that, press graph. On a T89, you press diamond F3. You hit enter, and you're waiting for this graph to come by. You don't see any of it. But if you press the trace button, which is just F3 now. If you're looking at the window in a T89, you press F3. On this calculator, you just press the trace button. You'll notice here we see X is 5, Y is 299. And as we start to move to slightly bigger values of X, we're getting bigger values of Y. So you can tell that my Y max is not big enough. So we should go back to window. I'm going to go to Y max, and I had a number like that was 300. So I'm going to go to, I'm going to go to 500 here and see how that works. And this is sort of how you play with windows to see, what's going to work best for you. Hit enter, press graph, and now you get to see a lot more of this picture, and so forth. Now you should take a minute to try and figure out what this means. So if you press trace, you'll get back numbers. So for example, if X is 5, remember X was the radius. So what this is saying is if the radius of our can is 5 centimeters, we can expect a surface area of 299 centimeters squared, right? Now what you'll notice is that you can move right and left on this. If I make the radius bigger, that means that my can is it's going from something like this to something like this. This is an exaggerated view of small increase, but what I'm doing is if I increase my radius, I'm making a can that's wider but shorter. Okay? And what this graph is telling me that by doing that, by going from say 5 to 5.425 centimeters in radius, I end up a bigger surface area for my can. When we think about it, that means I have to use more material to make my can. The surface area is bigger. So somewhere to the left of that, if I keep moving to the left, I'm going to get near a point where there's sort of a minimum surface area. You can see I'm down to 286, so I've saved myself quite a bit of aluminum to make this can. Also have to think about the millions and millions of cans of drinks that are sold every year. So any savings I can figure out is going to get multiplied by however many cans I sell. So it's to your advantage to try and minimize these things. Okay, so I'd like to know where that minimum really is, which is another part of the question. So to do that, it depends. On the T84 here, if you do second trace, which is the calculate menu, on there, you go down to the third thing, it says minimum. On the T89, press F5. If you press F5, we'll get a menu, and on there is the word minimum. So we hit enter. The TI-84 will ask you for a left bound. The T-89 will ask you for a lower bound. Lower and left mean the same thing. Go left of where you think the minimum is occurring. So you'll notice I have my flashing cursor over to the left of where I think the lowest point of this graph is. I hit enter one time. And it's going to say right bound on the T-84. It'll say upper bound on the T-89. Move it right of where you think that minimum is occurring. If you have any doubt, just go a little further to the right to make sure you're definitely right of it. So I would say that cursor is now right of where the minimum value is occurring. I hit enter one time. This will ask you for a guess. Don't worry about that. I hit enter, and now I have an answer. So what I know is that this minimum point here has coordinates 3.84 approximately, 277.55 centimeters squared. So we can convert that into a sentence in the context of the question. We could say that when the radius of the can is 3.84 centimeters and it has a volume of 355 centimeters cubed, the minimum surface area would end up being 277.55 centimeters squared. It's a very popular optimization question. So here's sort of an interesting fact. A real soda can, right, has a radius of 3.25 centimeters. Now we got to keep in mind the real soda cans also are not perfectly cylindrical shapes because they've got that little like concave wedge out of the bottom and they've got a sharp crease on the top and so forth. So they're not perfect cylinders. But clearly if the real radius is that, for a 12-ounce can, which we know corresponds to a volume of around 355 centimeters squared, cubed that is, but they're actually using too much aluminum, or more than they really need to. They should have a more idealized radius, right? You might ask why that happens, and there could be lots of reasons. Maybe it's packaging, maybe it's shipping, maybe those cans are shaped a certain way because they're less likely to get crushed when being packaged or stacked on top of each other. There's lots of considerations. One more fun thing, if you consider the idealized answer, we had a radius, I think, of around 3.84, right? We knew the volume was 355. If you plug that into the volume formula, you get 355, oops, hold on a second there, 355 equals pi r squared, 3.84 squared, times h. And if you take a minute to solve that, see what you... So 355 divided by open, we got to divide by pi, times 3.84 squared. Oops. Squared. Hit enter. And we get this number, 7.663 about. So the height's about 7.66. So that means our idealized can has a radius of 3.84 and a height of 7.66. You might notice that if you take 3.84 and double it, right, you get about 7.66. So this is sort of an interesting thing. What this is really telling me is that the idealized can should be just as wide as it is tall. And that would use the minimal amount of surface area.